This is Mark Richardson. This is our monthly webinar from Vibrant Technology here in Centennial, Colorado, a suburb of Denver. And we're going to talk about route-based data collection today and what we can do with it in MEscope and how we can make videos of the animation of ODS data that we've collected in a route-based program out in a factory or a plant. This is a very common way to do monitoring of machine vibration, condition monitoring. Typically vibration is measured, but temperature and other variables could also be imported into MEscope and used to document the condition of the machine. So the whole idea here behind MEscope is that we can make a video of a comparison display, and what you're seeing here is a comparison of what we call a baseline ODS on the left and some current data on the right. Now, in fact, this ODS is exactly the same on both left and right, as indicated by this bar over here, which is what we call our shape difference indicator. When that bar is equal to 1, that means the two shapes are identical, and when it drops down from 1, they're different. So this is a way to graphically show the difference between baseline data, let's say the data that was recorded when the machine was balanced and was aligned and no soft foot or any problems with it, and then some current data that would be taken. So that's the whole idea. I'm going to go here and make a video. This is what we want to record from the animation. Now you can see the animation is very exaggerated, and this data did not come off of this particular machine. So to use the term that our president now uses, this is fake. This is not fake news. This is fake data. We did take it off of a rotating machine here at Vibrant, and I'll discuss the details of that when we get further along in the webinar. But I want to show you the kind of the end result here first, and that is that we can make a video. Now, these are called hotkeys. They're a standard part of MEscope now, and I've created each of these hotkeys. You can see the first one is called Start Over. The next one is called Next Point. So we're going to walk through each test point on the machine and take data. We're going to import data. Now, since we're not hooked up to a data collector or an analyzer, this is all simulated. I'm going to show you how the acquisition window in MEscope can acquire data out of a data block. So we've got some pre-recorded time records of this machine, and then we're going to acquire them into a data block and post-process them into what we call ODS FRFs. And that's a hybrid between an auto spectrum and a cross spectrum. We use the auto spectrum together with the phase of the cross spectrum between each of the blue cubes. Those are the test points on this structure, and the red cylinder, which is indicating a uniaxial accelerometer, and that's our reference. So that one doesn't move, but as we take data, we go from the blue cube here on the motor to the next blue cube and so on. So we'll go through that in a minute to show you how the data is collected. Now this would be a simulation with a 4-channel analyzer where the cube is a Trax or Excel, and the cylinder, the red cylinder, is a single axial, uniaxial Excel, my reference, and the blue cube is my roving. So with a 4-channel portable data collector, I can collect this type of a data one point at a time, one roving Excel position at a time. This is a common way to do route-based data collection. After we look at this, then we'll look at how we can do the same thing with a two-channel analyzer, where one, and there we would just use two uniaxial accelerometers. One's our reference, it doesn't move, and the others are roving that would move to each of the positions where we want to measure the ODS. So let me go ahead and make a movie here, and this is kind of the end of the story, and then we'll go back to the beginning. So we're comparing these shapes right now. I press this hotkey and that will basically show me the same thing. And now I go to the next hotkey here. Well, the next one says new baseline. So we'll go back and use that one to set the left-hand shape data as our baseline and compare that with the right hand. And then we'll record some data that shows a difference between the two. I'm going to make a video here. This is one of the features in MEscope. Now what it's done is made the window a little smaller, and now I start the video recording. So this is the way that we think will be used in the future, more to record the condition of a machine. And we don't have sound added to the video yet, but that's the next step here at Vibrant, to be able to document a machine's condition with an animation like this. And I can interact with it. I can change my view position. I can actually go to what we call the quad view here, and then maybe just switch over to the top view and then talk about a problem that may exist on the machine and send this video to the operations department along with my explanation for why maybe this machine needs some maintenance scheduled for it. So that's what we're doing here with this video recording, and as I've been speaking here, it's been recording the animation that we're looking at here. And then we'll just go back to the 3D picture here. And let me stop that recording. So MEscope has now made a recording. You can see it's kind of exaggerated. You wouldn't want to show this to operations. They'd say, well, boy, you took some bad data there. But you get the idea. Okay, so there's the video, and I can stop it and play it back and so forth. This is a Windows movie file that I can email to operations. I can put it in the database and keep it to record this current day's collection of data. Okay, well, let me close that and let's start over here. So I'm going to go back here and push the first hotkey, and that's going to execute a script. And basically, here's what it did. Now that script, we'll maybe get into looking at some of these scripts. This is a standard part of MEscope now. A script is just a spreadsheet of MEscope commands. And of course, the first command here rearranged all the windows so that I can just look at a few things at a time. So on the left is a picture of the model, and you can see that there's some labels. Here's my first test point. It's number 1, and it's actually showing me the orientation of the accelerometer. So it's showing me how to put that accelerometer on there. Typically it would be magnetic, could be fastened other ways, but the operator would know that this is how that accelerometer needs to be placed on that machine so that the data that's collected would match up, at least in the degrees of freedom, the different directions, with the baseline data or any other data that's been archived in the database. Now if I press this button here that says next point, you can see that it moved over to the next test point, which is where I would collect data. So if I had this software in a mobile touchscreen device, I could take it out in the field with me and actually use this model and use this software to help me collect the data and then put it right into the database. I'm going to collect the next one here. You can see now it's going to point number 3, and X, Y, and Z are all indicated, and I can interact with this 3D model, and it shows me exactly where to put the accelerometer. Here's the fourth one. Now that one, because of the location, the x-axis is in a different direction than it was for the previous test points. Let's just walk around here again and see there's point number 1 and number 2. So each time I press the hotkey, it moves the display to the next point. Now what's it really doing? Well, here's the acquisition window over here, the MEscope acquisition window, and acquisition is actually telling the model which point to display. And if I look down here in the channel spreadsheet for this acquisition window, I'm on point number 4 right now, so you can see the degrees of freedom for this test point are 4x, 4y, 4z, and 5z. 5z is the reference. And so let me pull this over here and we can get a little closer look at how this is set up. Now in our terminology, an output would be, in this case, the roving accelerometer, and the input would be the reference accelerometer. So we use this, we call it MIMO, multiple input, multiple output. When we're measuring ODS FRFs, it's a two-channel measurement. It's not really an input and an output, but we use the same terminology here. So an output is a roving accel, an input is a reference or a fixed accel in this case. And you can see up here the measurements that I'm making are ODS FRFs, and I'm going to make those by computing them from these time records, and we'll get to that in a second, but the time records up here in the top of the acquisition window are the raw data that's coming off of the accelerometer. So you can see there's 4 channels there of data. If I scroll through, those are the 4x, 4y, 4z, and 5z. So those are my vibration signals. Down below here is an ODS FRF, one of the 3 that are computed between each of the roving transducers or sensors and my reference accelerometer. So if I scroll through here, you can see this is a magnitude plot of each of the ODS FRFs. You can see the first one is 4x with a colon and 5z. The colon 5z is indicating the reference. And then here's the second one. And you can see the cursor is set up here around basically the running speed of the machine, 2000 CPM or RPM. And there's a peak cursor turned on because the ODS that we're going to extract from this data is the peak values of the spectrum at the running speed. Now I've got running speed data here. I've got multiple orders, but this data was taken, as I said, from a rotor kit we have here at Vibrant that had a slight unbalance in it. So the first order, or the running speed of the machine, is going to show up as the largest peak in the data. The other thing I notice here is that we're taking accelerometer data. So the data that's coming in from the end of the front end is in G's of acceleration, but if we look down here at the units, the acquisition window, since we're displaying units in inches per second, we're actually integrating this data so that its units are inches per second, which is the common units of vibration data for machine maintenance. You can see that I've only got 4 channels turned on here. There's actually 14 channels. So where's that data coming from? Let's go and import some data now. So I'm going to press this button, this next hotkey here, and it will change the picture so we can look at how the import is actually working. Now, if all the signal processing were done in an FFT analyzer or a portable data collector, then I could simply program MEscope to import the data from a disk data file. In this case, we're importing it from a data block, and this is the data block here with the time records in it. And you can see there's 14 of them. Well, no, there's 12 response channels and then the reference down here. So 13 channels of data. And you can see the measurement numbers, which we use for animation and so forth. Number 6 was actually 0.2 in the Z direction. So if we go back to the model, that we're just using that data to simulate the reference accelerometer, and we're calling that 5Z. Here's all the data in G's. Here's our data down here in the data block after we've processed it in the acquisition window, and you can see that we saved 3 measurements down here for 4X, 4Y, and 4Z. So those are the measurements that got saved when I pressed the hotkey that said import data. Now the other thing that happened was that out of the acquisition window we saved the peak values at the running speed, and those values went into a shape table over here, and you can see the 4 values in inches per second for the 0.4 in the X, Y, and Z. So let me just go through this again and we'll watch what happens. So I'm going to press this over again. We're still on 0.4. Now watch what's going on here. It's actually averaging some of this time record. It's acquiring the time record, averaging it in the frequency domain. So I'm taking 3 averages. Well, how do I know that? If I come back over here into the acquisition window under measurements, you can see that I've got it set to 3 averages. And there's some other parameters in here, but it's all set up and been saved in the programming, in the scripting, and in the acquisition window itself for this project. You can see I'm acquiring 2,000 samples of data. This data block here was recorded and it has many more samples in it, but each time I press the import data, it will start from the beginning and collect 3 samples of data from those 3 channels, and then post-process and put the data into the data block and so forth. So how does this work? Let's go back and just walk through a whole scenario of acquiring data. So I'm going to set it back to point number 1, and then I'm going to import the data for point number 1. And we'll see that, bingo, I saved the data here, I saved the data here. Now I go back and collect the second point, again import that data, and it's going to go back through my time records and just pull out the data for point 2 and save it both here in the data block. So I've got the spectrum data that I can log in or archive in my database, and also the shape table. And let's go on here and do it for the third point. Press the button, and acquiring the data for point number 3. So you can see it's stored it here, it's stored it here. So this has all been automated in MEscope to do this route-based collection. Okay, so now once I've got a set of data like this, I can go on and compare shapes. So we started out doing that. And so here we are back to the animation where we're comparing the baseline with the data that we just acquired. So what we're animating here, this is a comparison animation of 2 shape tables. The one on the top is the baseline, and the one on the bottom is the data that we just acquired. Now they're identical, and the reason is that if I go back here and look at the import, we're always starting from the beginning and walking through the same set of data. Well, what if we took some data out here that's a little different, and that would simulate maybe a a change that occurred in the machine from the baseline data, unbalance, misalignment, soft foot. Those are three common occurrences in a motor pump situation like this. So I'm going to go in here and hold down my control key, and we're going to look at, here is the script or the program that runs every time I press the key called import the data. Down right here is a command that says go into the data block called medium run up 38 seconds. So this is actually some run up data where the frequency is going to change in the data. We didn't see that so much in the beginning, but let me just take this command out. If we look at that command, what it's doing is resetting the band cursor to a percentage of the screen, 0 position. So that's resetting it back to the beginning of my data block. I'm going to just turn that command off so it doesn't do that. And now I can move the band cursor anywhere I want, and the acquisition window is going to pick up some of this other data. Again, this is a simulation. So now if I run this import the data, you can see that it's walking further out into the data block. So let's go collect a set of data that's, let's just put it way out here. I'm not sure where the real physical changes would start to occur. You can see some bumps in the time record here, and can't tell much from the time record, but let's go back and take another set of data. So here we'll start at point 1, acquire the data, and again we're importing, and so we didn't reset. I'm going to go back and move to the next point, import the data, and we'll just let it keep walking along and randomly take some different data for each of these test points, and then we'll see what the shape looks like after we're done here. And here's point number 4. I'm going to import that data. So again, we're simulating a case where we went out and took some new data on the machine. Now let's go. We've got a new set of data. You can see we've saved the 4th one in here. And you can see the peaks are moving around a little bit because this was some run-up data. And over here in the ACK window, we actually turned on the peak cursor with a peak finder function that will find that peak in the data and then save the peak values as the ODS data over here in the shape table. So this is our new set of data, and now if I go into compare shapes, I'm going to compare it with the baseline, and we got a different shape. Well, you can kind of see from the animation, the point up here on the pump is certainly moving a little different, but our indicator here, our shape indicator, has dropped to a value of what, 78%. So that is indicating to us that these two shapes are different. And rule of thumb is if the difference drops below 90%, that's a significant change. We could even say 95% is anything below that would be a significant change in the condition of the machine. So there's a lot of things we can do with this data to compare these, but I may want to just go ahead and make a movie. And same as we did before, we're going to record this change in the ODS of the machine. And as I said, we can archive this data. My last hotkey here is an archive command, so we can archive this into a database. We can reset the baseline if we brought this machine back online after maintenance, take a new set of data, save that in as our baseline shape, and then continue on with route-based collection on this machine, and we can literally save. We have a new database in MEscope that's unlimited. Well, it's limited only by the storage capacity of the computer. So I can take this type of data out in the field with me in a mobile device, mobile touchscreen computer, and collect this data and make these videos as I'm taking the data. So let's finish this. And so here's the video of the before and after, the data that's been collected. And again, with audio on this recording, we can certainly document for the operations people what we found, let's say this week or this month, by looking at the first order response of this machine. Okay, well let's go to the other case where we only have a two-channel analyzer. Now we have to have, in order to look at these ODSs and compare them and so forth, we need magnitude and phase between all the test points. And the way we get that is to measure the phase between all of the roving points and a reference point, and that way we have the correct relative phase between all of the roving points. Now remember how I set this up. It's all a simulation, but I just picked the response of, let's go back here to the animation. I'll push the comparison button again and we'll get the big picture back. Let me put this guy back up here in the corner. And remember, I simply artificially took the Z direction motion of number 2 here, and I assigned it to the uniaxial motion of what we call 5Z. So again, just to simulate things and to use some recorded data. Let's go and close this project. So I'm going to close the project. No, we don't need to save it. And now let's open up another project called a two-channel motor pump. So what this project has in it, same set of hotkeys. Now I don't have a hotkey to make videos, but I've got one to start over. So let's look at that. And so here it is. It's opening up a number of windows, but it's come back with the same display of the acquisition window here, some data up here on the top. This is the recorded, pre-recorded time histories, and you can see here that now it's telling me, okay, here's my reference at 5Z, and here is my first measurement with a uniaxial accelerometer, 0.1 in the X. So if I only had a uniax, I'd have to somehow mount it there. Maybe I have a little tripod gadget I stick on the motor, and so if I use a magnet, I would simply put the accelerometer in the horizontal direction like that. So let's just hit this hotkey here and walk along, and you can see there's my second measurement. Now this, in order to see a little more clearly, we've actually hidden or made the model transparent so that when you're out in the field you can see clearly, okay, this is 1Y, that's my second measurement. And we could label these as 1, 2, 3, 4, 5. Here I haven't changed the labeling, I've just left them as 1X, 1Y, and 1Z. We can label these any way we like in MEscope. Now we're over here at 0.2 in the X, and 2 in the Y, and 2 in the Z. Yeah, there's 2 in the Z. So you can see that for a two-channel analyzer, it's a little more work. now instead of just 4 measurement points, I've got 12. And so I've got to go through and move this thing and take data at 12 and make 12 measurements in order to get the same results that we got with the 4-channel and only 4 measurements. So that's the advantage of having a little bit more expensive equipment. But MEscope works pretty much the same way. It's actually quite simple here. Let's just go ahead and take some data. We're out here 4 in a Z. I'll just record this data here, and you can see it's popping up some scripts that were closed, and okay. All right, I just recorded the data, and where did I record it? I don't see it. Oh, here it is down here at point 11 and point 11. So 4 in the Y was where I had my indicator set. Okay, 4 in the Z, let's go. Oh, you see I got a previous button here, so I can go forward or I can go backwards if I take some bad data. And so this is set up to do that. Now you can see that it's recording out of the beginning of the data block here, the pre-recorded data. So when I get to the comparison shape, even if I haven't collected all of the data, it's probably going to match up with my baseline. So here we're over at 1x. Let's import some data. You see there's a little more work with a 2-channel, but you can still do the same sort of thing here in MEscope. Let's go compare the shapes. So here they are. And you can see that, gee, my baseline is quite exaggerated here. A little bit different result. 0.2, apparently I had collected some data further out in the data block. But you can see that so far nothing has changed. It's all the same. Let's go to 0.2 and actually collect some data there, and it should change from the baseline to a difference. Okay, so we're at 0.2. No, we're at 0.1. Let's go to let's go to 0.2 and collect. We'll collect the 3 points at 0.2 and see if those are actually different than the baseline. So let's import that data. You can see it went back to the beginning, and then we'll get the Y data, import it. And back, and let's get the Z data at 0.2. So you can see this data is going in down here, 2 in the Z, it's stored in here, 2 in the Z in my ODS. So I've got not only spectrum data that I can archive in the database, but I've got some new shape data. So let's go and compare shapes now and see if we don't get something different than the baseline. Oh yeah, see, this baseline here was recorded somewhere out in my data block of time records, and now when I went back and got some new data here from the beginning, you can see also that numerically they're 91% alike, but that one data point has caused the SDI value to drop because of the difference in the ODSs. So that is all I had to present today. Brian, do we have any questions from the audience, from the viewers? Brian Schwartz is my my manager here today, so he's kind of managing the recording for us today. And
No questions yet.
all right. Well, if there are no questions, that really concludes our presentation today. Not quite an hour's worth, but I wanted to show you how we can use MEscope for post-processing route-based vibration data. And we simulated some post-processing here, including our acquisition option to MEscope, which can read data from a data block, or it can read it from a front end if the computer were actually hooked up to an acquisition front end. In this case, we simply read it out of a data block of pre-recorded data for the 4 different test points on this machine. And again, it was fake data. This is not data off of this machine. This is data off of a rotor kit that we have here at Vibrance. So don't be alarmed by the picture you're looking at. We're simply trying to illustrate capabilities in MEscope. And again, if I go back and make videos, I can't make them from this project, but I can make them from the previous 4-channel project. That's really what I wanted to show you today, a way that we can use the ODS animation capability and the video recording capability in MEscope to go back. And now I'm back in the 4-channel, and I'll just go right to the comparison animation. So the whole idea here was that we are comparing baseline and current data, and I can go, as soon as I have this picture, I can make a video of it, and as soon as I start the video, it will document for me a comparison between a baseline ODS and data that I may have collected today or more recently in the field on this machine. So we're making changes to MEscope. As I mentioned, we've got a new database under MEscope that will save as much data as the computer can hold. So in a route-based program, maybe we have data for 50 different machines that one analyst would collect data for, and he could make a video like this for each of his machines that he is on his route, and then that data could be put into a larger database back in the office after he's collected data. But out in the field, he's got all the capability to make videos like this, and as I said, with sound recording, document the problem for operations or for management to make a decision based on this recording about the maintenance of the machine. All right, I've said enough, and thank you for coming, those of you who attended. And next month we're going to, not sure what the topic's going to be. I think what we're going to do is expand or show you how we can use this SDI measure here. And we're going to use it to compare spectrum data. Here it's being used to compare ODS data, but we can actually use it over a band of frequencies between baseline and current spectrum data. We didn't do anything with the spectrum data here today, but we can do a comparison over different frequency ranges using this same metric. So I think next month we're going to show you how that all works. Thank you for coming. Brian, do we have anything else to add?
No.
All right, well, we're wrapped up for today. See you next month.